Significant figures. All right, so when we measure something, it's different than counting. All right, so the issue we have is we're used to counting, right? So when we count, right, I know how many pens you have in your pocket, or how many quarters you have, or how many phones you own, or how many computers are in your house, right? We can count these things, right? How many people are in your family? How many cars do you own? All right. So counting is totally different than measuring. All right. So we're used to counting. Well, now we have to do measurement. So Sig Figs, when we measure, there's a big difference. So there's a difference between 20 degrees Celsius and 20 degrees Celsius. And that might sound very silly to some of us, but it's not. All right. And one of the first examples I can use is if we're driving. So if you're driving a vehicle down the road and the speed limit's 45 miles an hour, and you happen to be going, let's say you're going 52 miles an hour, right? And all of a sudden, right, you see it, and there's the police officer. And as he goes by, you can tell the lights flashed on. And you get that sinking feeling that you know you're probably going to get pulled over. Now, maybe you are, maybe you're not, right? But let's say this time you did, and you get pulled over. A lot of times we will, wait, get your registration, proof of insurance out, your license, all ready to roll. You're waiting, roll down the window, and here comes the police officer. And, hey, how you doing? You know why I pulled you over? And gives you a chance to admit guilt right there. And they say, yeah, I was going a little too fast, wasn't I, sir? Or ma'am. And the police officer says, yeah, I got you at, how fast do you think you were going? And a lot of us will tell, 50, right? You try to do the sunny side of the truth there, because there's some error in measuring, right? Because maybe the radar gun was off by a mile an hour or two. So we tend to do that, and that shows measurement, because you're not counting how fast you're going, you're measuring how fast you're going. And so you have a speedometer that measures how fast you're going, and the police officer has radar that tells you how fast you are going. And so do those match or not, right? And that's an example of where measurement comes into real life. Another way measurement comes into real life is if you're doing any type of home renovations, new flooring, right? You'll learn real quickly that your house is not square, right? It's close, but it's not perfect. All right. And so when you measure and you're putting in flooring or walls or anything, like sometimes there's some error in those measurements. All right. And so we need to include in our answers. So when we're using data, right, measurements, when we include into a report, we only want to use the number Sig Figs that is justified. All right. Okay. And so how do I know that? Okay. And that goes into how many Sig Figs are in a number. All right. And so we're going to ultimately learn the difference between placeholding. Oh, let's go here. Placeholding. Placing. How about place holding versus measured zeros. That's the big one, all right? And so now we're going to round off at the end. Most of us have these nice graphing calculators or spreadsheets or whatnot, and they can round at the end. So we'll round at the end. All right. So our big goal is to figure out whether we have placeholding zeros or measured zeros. Okay. And that's a big deal. Okay. And so if there is a decimal point in the number, we draw an arrow from left to right until you come to the first non-zero digit. So left to right. So if there isn't, right, there is a decimal, so left to right, boom, 8. So that means everything significant there. The 8, the 2, the 3, the 0, the 1, They're all significant, so there's 5 significant digits. Like 8,230.1 grams. That's a good number, right? You can measure that. Here, all right, there's decimal left to right. I only have 4 significant figures. These are, those 2 zeros are placeholders. They're very important, all right? So, for example, I could make this number 5.041 milligrams. I can actually weigh that, right? Think of a pill, a 5.041 milligram pill, a 5 milligram pill. All right. The thing is, those 2 placeholders are very important, but they're not measured. Does that make sense? So the order of magnitude is very important, because if you're taking a 5 milligram aspirin, that's totally different than a 5 gram aspirin. That's right. And so it's important, but it's not measured. So there's no data there, right? If you have if something 5 milligrams on the scale, there's nothing else on the scale to measure, so you have no measurement. So there's nothing significant there. It's important, but not significant. All right, it's not measured. The other option is that there is no decimal point in the number, right? So the decimal point here would be right there, but it's not listed. So then we draw the arrow from right to left. All right, and I have 5 Sig Figs. 1, 2, 3, 4, 5. Now, these other ones are placeholders. So these 3 are, again, are placeholders. They're very important, but they're not measured, right? So, like, if you won the lotto tomorrow, 55,041,000, that would be great, right? Okay, but 55 million is what we care about, right? Let's say there is some numbers down here, you wouldn't bother you if what they were, right? If you lost, taxes in general, but if if it's $20 down there at the end, it's not that big of a deal. You care that there's $55 million, right? And so those 3 placeholders are very, very important, but they're not measured, because there might be stuff down there. Because if you went to pick up your lotto ticket and it was 55,000, I'm sure most of us would take it, but it's not 55 million. Big difference, right? And so the placeholders are very important for a number, but they're just not measured in the number. All right? And so when we have a measurement, we want to know how accurately is that measured, right? Because that's an important thing, right? How accurate is my measurement? Okay. So before we do that, a little note here, right? All numbers written in scientific notation, I spelled that wrong. That's just are significant. So, what does that mean? That means if I have 5.4 times 10 to the 4th, or let's just say, 5.39978 times 10 to the 4th, right? These 2 numbers are significant. Well, I don't use that color. Let's use green. These are significant. And all of those are significant. And by the way, that 10 to the 4th, that's exact. And that's also exact. All right. So let's do a couple examples. How many Sig Figs are in these numbers? All right. So if we look at this first one right here, the 00105. So there is a decimal place. These 2 are the placeholders, right? anytime I have a 0 between the two numbers, I'm going to have 3 significant figures there. And again, these two are the placeholders. They're very important, right? That's 1.05 milligrams or 1.05 milliseconds. 1.05 milliliters, whatever it is. Okay, it's important. So we need to know the right spot of our measurement, but they're not measured. If I go across, right, there is a decimal point here. So this number, if I remove that last 0, guess what? It doesn't change the number at all, does it? So here, they're all significant. All measured. So that's 1, 2, 3, 4, 5, 6. All 6 of them are, right? Because if I remove that last 0, it doesn't change the number at all, right? So that's like 10.0010 grams. We can actually measure that, right? That's a measurable number. And so, all right, it's the difference is if I take these placeholders away, I change the number value. All right, I make 0.01 versus 0.001. That's a 10 times difference, right? Where here, if I take that 0 away at the end, it's still 10.001. It doesn't change the value of the number at all. All right, so that's another way to tell, is it a measured 0 or is it a placeholding 0? 0.08206. All right. So hopefully the 0 before, we know this, highlight this 0 right there, that one is not going to be important. That's just to show us that there is a decimal point. My pen or pencil didn't accidentally just hit the paper there, right? So it's a good way to communicate it's 0 point something. Now I have two other zeros because obviously the 8, the 2, and the 6 are all significant. Which one? All right. So now the 0 between the two numbers is going to be significant. The 0 that's in front is a placeholder. All right. That's a placeholder. And so in this case, it looks like we have 4 Sig Figs. 1,000. All right, 1,000. Well, how many Sig Figs is that? 1. Those 3 are zeros are placeholders. All right, that's 1,000. All right, could it be 1,100? Could it be 900? Somewhere in there? Sure. Okay, right? We don't know, and so that leads us into what we call ambiguous numbers, which hopefully are coming up. But that's kind of ambiguous because right now it's 1. It's probably more than 1, but we don't know that. The best way to communicate that would be like 1.00 times 10 to the third, or 1.0 times 10 to the third, right? Because then I'll know it's 3 Sig Figs, 2 Sig Figs, right? Or even 1 times 10 to the third. Then it's 1 Sig. I know it's 1 Sig Fig, right? Because we don't like ambiguity. We like to know exactly what's going on. All right. So when it comes to this, all right. Oh, I didn't on here. All right. So I got to add these. So first is ambiguous, which we just kind of talked about, right? Which is we are uncertain on, right, the number of Sig Figs. And you want to use scientific notation to avoid. All right, we're going to make sure we do that. Because otherwise, like why? Like, for example, 10,000 meters. Well, that looks like there's 1 Sig Fig. Chances are it's not. So what I would want to do would be like 1.000 times 10 to the 4th meters. Then I know I have 4 Sig Figs. Right? I might be off by 3 meters, and that's okay. It's still 10,000 meters. I'm not off by 1,000 meters. that's a whole kilometer. And the last thing we need to talk about are exact numbers. Right? And these are no uncertainty. So there's no uncertainty. There's no error, all right? So what are they? An accurate count of discrete objects. Right? So if I have an accurate count of discrete objects, let's say we have 7 quarters, 3 dimes, and 2 pennies. I have what? 12 coins total. There's no like, well, was it 13? No. I have 7 quarters, 3 dimes, 2 pennies. I know exactly what I have. That's no uncertainty there. All right? Define quantities. For example, 1 inch is 2.54 centimeters. That's an exact quantity. All right. Okay, and so there's no like, oh, I only have 1 sig fig now. Nope, that's an exact right definition. You have infinite sig figs. And last, right, integer numbers that are part of an equation. So the volume of a sphere is 4/3 pi r cubed. Well, pi is an irrational number. The radius is measured, but 4 and the 3 are actually they're whole numbers, right? They're exact numbers. They're not going to add or subtract to the sig figs. All right, and then so thus far we've just looked at. All right, when I have a sig fig, how many are on the paper? All right. When we use data or sig figs, data measurements with sig figs, we got to figure out, well, what can I report to? So that leaves us to addition and subtraction versus multiplication and division. All right, those are the two operations, right? Addition and multiplication. So when I add or subtract, the final number should always have the same precision as the least precise number, which means I go to the right as far as possible. All right, we go to the right as far as possible. I want to go to the right as far as possible. So if I look, it looks like as far as possible is right there. All right, the 10th spot, because everything has the 10th spot. It doesn't matter if I don't have data out here. That's okay. But it does matter that there's nothing there and nothing there. That makes sense? So I can only go to this spot. Right? And when we round, I look at, since this is where we can round to, I look at that 3. And since it's a 3, I keep my 5 of 5. Right? So it doesn't matter if I have something like XYZ point, 4, and then it's, if I can go to that number, and this is 499999, right? I'm only looking at this 4 for that number. Doesn't matter that it's 499999, right? That's how we're doing it. So when we add and subtract, we go to the right as far as possible. That's it. Okay. All right. So that's why we can add, like say, 14, 17 plus 100. All right. I can add that to make it 114, 17 in money. It works that way. All right. Because, $100 bill is an exact number. Multiplication and division, a little different. All right. Okay. So when I add and subtract, if I'm off by a little bit of distance, let's say we're finding a perimeter of a desk, right? So you're measuring your desk or table, and you're going to measure the distance around the edge. Let's assume it's mostly square. right? I don't know if you're at a kitchen table or not, but let's just assume your table or desk you're sitting at square. You're going to measure the length and you're going to measure the width. All right? And the length and the width, and you'll get the perimeter. When you add those numbers up, or you add the length, the width, the length, the width, all the edges, the error is added. If you're gonna, the error is added. Now, if you're going to find the area of the desk, you take the length, the width, and you multiply them. Your error is now multiplied. It's compounded. All right, and so it's why measurement and the error is a little different. Okay, so it's the level of precision is determined by the total number of Sig Figs rather than the number of decimal places. So the answer always has the least number of Sig Figs. All right, so the number with the least number of Sig Figs limits us. So 12.1 is 3 Sig Figs. 10 is 1. So my answer can only have 1 Sig Fig, which seems weird, right? So that's 1.21, which my answer is only 1, because I can only have 1 Sig Fig, which seems like we lost information, but not really. Not really. We didn't really lose any information. We didn't have the information to begin with. 12.1 is pretty accurate, let's say, or pretty precise. But 10 is not. All right? 10 is not. So, all right, you didn't have the information, so you didn't really lose any information. Now, 10.0, I would keep all 3, but I don't have 10.0. So that's why measuring is so important. So when we're, especially in your lab, measuring is very important to write down the accurate measurement. All right, I see this so many times where, let's say that was 10 degrees Celsius. 10.0 degrees Celsius is different than 10 degrees Celsius. Right? Why? Well, we have 3 Sig Figs versus 1 Sig Fig. Huge difference. And now what happens? All right. Oh, there's my exact numbers. I knew I had them on here. And there's, all right. Accuracy and precision. Now let's talk about this, because this is also very, very important. All right, accurately is how close to the true value you are. All right, how close. And precision is the degree of agreement among several measurements. All right, I happen to be close to a military base, but whether it's shooting with a firearm, whether it's playing basketball, playing baseball or softball, right? Obviously, we want accurate and precise right here, right? That's the one we want in green. That's accurate and precise. It's repeatable, right? Okay. The second best one to have is precise, because we are doing something systematically to move this group to there, right? I could do that. Whether I'm shooting free throws, right? Playing basketball, shooting free throws, and I'm constantly hitting the front of the rim, right? Same spot over and over again. Well, we can probably do a small adjustment and make the ball go in. But if I'm shooting free throws and I'm all over the place here, right? I'm hitting the front of the rim, I'm hitting the side of the rim, I'm missing the rim, I'm hitting the backboard, right? Okay, we got a lot of work to do. So this is, all right. Now, you can also make it, and we didn't have this here, but like if this is another box, I could technically have here, here, there, and there, right? And so if the bullseye is right in the middle there, that's technically accurate, because it's the average, right? The average of the top and the bottom axe is right in the middle, and the average of the left and the right axe is right in the middle. So that's technically, there's my average. The average is real close to the accepted value. It works out, okay? But that's not what we want. That's also bad, right? We want to strive for the green here. This is what we want to strive for, right? When we measure and accurate, right? Okay, is reproducible, close to what's expected. All right, and so, but that's the difference between accuracy and precision. And now, the reason I use that is if um, well, again, uh, let's say there's a, I don't know, let's say there was a hostage situation on this campus, which probably would never happen, but let's say there was a hostage situation on this campus and it was in the parking lot. You know, right? Um, if somebody had a sniper rifle to take out the bad guy, right, that would be you would need a very precise shot to be accurate. That makes sense, right? Because and if you be off by a few inches, you could totally miss. All right. If a pilot was trying to drop a bomb in the parking lot for some reason, again hypothetical, not going to happen. 2,000-pound bomb, it has to be close to the car, and the car's gone, right? So, but yet its precision is very, very low, but the accuracy is good, right? So the point with that is, if I just have to hit the wall, my precision can be very low and my accuracy is high. And so the more, like, the finer our measurements are, all right, precision and accuracy, they are harder and harder to get. All right, so the tinier your measurements are, the more refined your measurements are, it can get harder. So that's accuracy and precision. And recap temperature again. All right. So here's your scale where water boils, water freezes, absolute zero. Right, in Kelvin and Celsius have the same steps, as you can see. The steps on the scale are the same, 0 to 100, 273 to 373, it's 100. Right, Fahrenheit is not quite half of the Celsius, but it's close. And those are the temperature scales, and we will primarily use Celsius. All right, and that's where I'm going to stop.